Today, we're heading into orbit for a really high-stakes rescue mission. But the patient here isn't an astronaut, it's a satellite. And the doctor? Well, it's an AI, one that's been trained to diagnose an incredibly complex illness from millions of miles away.
I mean, really think about that. It's a wild question. When $1 billion piece of tech, something we rely on for GPS, for climate monitoring, for so much, starts to fail, you can't just send out a mechanic. So what on earth do you do?
For these incredible machines, a simple glitch can mean the entire mission is a total failure. They operate in this environment where there are absolutely no second chances. And right at the heart of their operation is the attitude control system, or ACS. You could think of it as the satellite's sense of balance. If that fails, the mission is pretty much over. So, to really understand the problem we're talking about, we first need to look at the pretty remarkable hardware that's responsible for this balancing act. It is an amazing piece of engineering that keeps these satellites pointed exactly where they need to go. They're called control moment gyros, or CMGs for short. And honestly, the best way to think of them as like a satellite's superpowered inner ear. They're these powerful spinning wheels that gimbal, which just means they tilt around on a support, to adjust the satellite's orientation with just incredible precision. This is what lets them point cameras and antennas with pinpoint accuracy. Now, to get the job done, satellites don't just use one of these. This research we're looking at focuses on a super common setup, a pyramid assembly of 4 CMGs, all working together in perfect harmony. This formation gives them full control and even a little bit of redundancy. But what happens when this carefully balanced system starts to break down? And this, right here, brings us to the core of our mystery. See, it's not about just one thing going wrong. It's about the chaotic, messy situation that happens when multiple things fail at the exact same time.
The problem becomes crystal clear when you compare a single failure to multiple failures. If just one CMG goes down, the symptoms are usually pretty obvious. But when 2, 3, or maybe even all 4 start having issues at the same time, their failure signals overlap, they mask each other. It just creates this messy, confusing stream of data for the folks back on the ground.
The researchers who wrote this paper put it perfectly. The complexity just skyrockets when faults happen in phase, which is a fancy way of saying at the exact same time. The effects of each individual fault just get tangled up, and that makes it incredibly difficult to isolate exactly which parts are failing and how badly.
Now, this isn't a new problem, but the old ways of trying to solve it, they just weren't good enough. The best methods could only manage about 67% accuracy. For a critical billion-dollar satellite, an accuracy rate that's basically just a guess, that's a failing grade. There had to be a better way.
And that better way, it turns out, involves a completely different approach. Instead of trying to untangle this mess with traditional engineering models, the researchers decided, hey, let's train a machine to spot the hidden patterns inside all that chaos. So let's call our solution the fault detective. It's a data-driven AI, a machine learning model to be specific, and it's not trained on physics rules. No, it's trained on thousands upon thousands of examples. Its whole job is to look at that messy data coming from the satellite and pinpoint the exact combination of failures. It's a task that's just proven to be way too complex for the old-school methods. The training plan had 4 key steps. First, they simulated hundreds of thousands of different fault scenarios using a super detailed satellite model. Second, they calculated the symptoms by finding the difference between healthy and faulty data. Third, they extracted key clues or patterns from those symptoms. And finally, they fed all of this info to the AI detective so it could learn to diagnose any problem thrown at it. But, turning raw data into something an AI can actually learn from is a huge challenge all by itself. It's all about identifying the right symptoms and then extracting the most important clues from them. So the process starts with calculating something called residuals. Now, I know, that sounds super technical, but the idea is actually pretty simple. It's just the difference between the data you expect to get from a healthy satellite and the actual messy data you're getting from the faulty one. These residuals are the raw symptoms of the satellite's sickness. But raw symptoms alone aren't really enough. They can be noisy, confusing. Our detective needs specific, reliable clues, what data scientists call features. After testing a bunch of methods, the researchers found that the most powerful clues came from a technique called correlation analysis. This method is amazing at finding the hidden relationships between different symptoms, and that reveals the unique fingerprint of each fault combination.
All right, so after all that extensive training on simulated data, it was time for the AI detective's final exam. How well could it actually diagnose a sick satellite in a test?
The researchers basically held a bake-off, testing several types of AI models against each other, and there was a clear winner. While other methods like neural networks and random forests did pretty well, a model called a support vector machine, or SVM, came out on top with over 92% accuracy right out of the gate.
But they didn't stop there. After fine-tuning the SVM model, they pushed its performance even higher. The final result was an absolutely outstanding 95.6% accuracy in diagnosing multiple simultaneous faults. This isn't just a number. For mission controllers, this is the difference between saving a mission worth hundreds of millions of dollars and losing it. It's a massive, massive leap from that old 67% limit.
And if we dig in a little deeper, we can see how the model does as the problem gets harder. For a single fault, it's nearly perfect, 99% accuracy. With two faults happening at once, it's still an excellent 97.8%. And even in the absolute toughest scenarios, with 3 or more concurrent faults, it still maintains an average accuracy above 91%. That's incredible.
Now, getting high accuracy in a clean simulation is one thing, but space is not a clean, predictable place. So the final critical step was to see if the AI detective could handle the chaos of the real world.
This is the make or break question, isn't it? Can the model still perform when the data isn't perfect? Because in space, it never is. Can it handle signal noise, sensor dropouts, and just the general unpredictability of a real mission?
To find out, they put the model through a pretty brutal stress test. They deliberately corrupted the data with random noise to mimic signal interference. They simulated entire sensors just failing without warning, and they introduced random gaps in the data, just like you'd get from a temporary communication dropout.
And the result? The AI detective proved its worth. Even when it was fed messy, incomplete information, it maintained a really high level of diagnostic accuracy. This robustness is arguably the most important finding of all. It proves the model isn't just some lab experiment, it's a tool that's ready for the rigors of a real space mission.
This achievement really opens up a fascinating final question. If we can build an AI doctor for a satellite hurtling through space, what's next? You think about power grids, commercial airliners, complex industrial machinery. What other critical systems are out there, just waiting for their own AI detective to keep them healthy?